Hi, Calc 2 students. In this video, we're going to continue our study of finding three-dimensional volumes by looking at a special kind of volume that's generated by revolution. So let's first try and visualize what these three-dimensional regions would look like. And this video is going to focus specifically on rotating regions around the x-axis. In my next video, we'll look at what it looks like when we rotate regions around the y-axis. So let's take a look at this first picture here on the left. We have some random arbitrary curve. We're going to just look at this in general. And let's say someone said, take the region that is described here, the curve y equals f of x, and the x bounded by the x-axis and the lines x equals a and x equals b. So that would give us this little blue shaded region here. And I've drawn in here a red rectangle because I want you to pay attention also to what happens when we take our rectangle that we would use to find the blue area and we rotate it along with our region. So when I rotate around the x-axis, you see the curve gives you the side of this cool little almost vase shape. And that rectangle right here, when it rotates around, it becomes a disc. So it's a solid disc with a certain amount of thickness, and the thickness here is the same thickness as the rectangle was. So a delta x value. Okay, so then what if we have a little more interesting, complicated region that is not touching the x-axis, like this yellow region here? Let's say it's bounded by two curves, so we'll just call the top one f and the bottom one g. And we'll look at a green rectangle, still rotate that region around the x-axis. And instead of getting a solid vase, we get almost like I guess still kind of like a vase shape, but it's hollow inside. So you could actually put something in versus the first one was completely blocked in. You see we have like a hollow opening. And the green rectangle becomes a washer. So washers are, hopefully my engineers, you probably know washers very well. Those little like stainless steel or many different kinds of materials of like almost a donut shape basically. It's used for all kinds of stuff. You can tell I'm not an engineer and I stay in the abstract based on my bad description of a washer. But our thickness here is still going to be a delta x because it is the width of the green rectangle is a difference in x values. Okay, so let's go ahead and look at how we would break down the volumes here. Okay, so let's look at each picture and think about how we would find the volume of that disk. So for the disk in our first picture, looks like we would find the volume of just that circular disk. And you might remember from a previous video, just refreshing the fact that when you have a disk, or otherwise known as a cylinder, I've heard it described as, disks. Disk is our preference for what we're going to call it. So anyway, we're going to find the volume of this. How do we find it? And you find the radius. Okay, what's the radius? The radius is the height of that rectangle. You can see the radius right here. It's the height of the rectangle, which should be given by the point that we use to draw the rectangle. So an f of x sub I minus the bottom, which is just y equals 0. So f of x sub I is going to be the radius. Okay, and we're using that subscript because this is just a general washer positioned somewhere. It's not any specific one that we've drawn. Okay, so the radius is f of x sub I. The thickness, we already said, is a delta x. And the area of the circle then will be given by pi times f of x sub I squared. That'll give me the area of the circle. So there's our a of x sub I function times delta x. There's our volume. Okay, the Riemann sum approximating the volume is you take all your disks and you add them up. You got the pi still. Delta x, and the I ranges from 0 to n minus 1, where n is the number of slices. Hopefully you guys have seen this now enough to feel comfortable with the fact that It's the same concept, just in 3 dimensions from what we were doing with approximating areas. So now that would give us an approximate, because remember when we draw these little discs, they're kind of jagged. They're not continuous as you draw them because the rectangle doesn't completely line up with the curve here. So that's just an approximate of the volume. To get the exact volume, we're going to go ahead and let n go to infinity and delta x goes to 0. So we could say as n goes to infinity, delta x goes to 0, and that becomes an integral. Pi f of x, the delta x goes to 0, and we're just left with the fact that we're integrating with respect to x. And when we do our limits of integration, remember the same concept holds true. It's from where you start your partition on your slices to where you stop it. So if we started our slicing at A and we ended our slicing at B, our limits would be from A to B. Okay, so carrying that same concept, let's go ahead and look at the volume of our ith washer that we have in green here. Okay, so for the washer, I'm going to draw it a little bigger than I drew the other one. The hardest part is going to be finding the actual area of the washer. Okay, so the thickness is still a delta x. We know that dimension. The problem is now we have, I'm going to shade this in black to remind you that this area that's shaded in, it's not actually part of the area we want to compute. So when we find the area, we're finding the area of the big circle and we're subtracting the area of the small circle. So the outer, it's kind of like we got an outer radius and an inner radius. The outer radius would be given to us by this red line, the height of f of x, and the inner radius would be given to us by the blue, which is the distance from the x-axis to the g curve. So we'll find the area of the big circle, which is pi f of x sub I squared. And then we have to take away the area of the smaller inner circle, which is pi times g of x sub I squared. And that's kind of a terrible way to write something, so we probably write it like this. You'd factor out the pi. And we tend to call the f of x the outer radius, and the g of x is the inner radius. That's what we call that. Okay, so that's the dimension, that's our area function, a of x sub I. So our volume of the ith washer is pi times f of x sub I squared minus g of x sub I squared delta x, and the Riemann sum would be adding up all of the washers. So pi times f of x sub I squared minus g of x sub I squared times delta x. And the index ranges from 0 to when you stop your partitions, and n is the number of slices. Okay, again, we're going to let as n goes to infinity, delta x goes to 0, and we get our integral from where we started our washers at A to where we stopped our washers at B. The delta x goes to 0, drops off, so we have pi f of x squared minus g of x squared dx. Just giving you a second to pause there and kind of think about it. Some students, I will say before moving on, some students really enjoy not drawing the cylinder or the discs and the washers this way. They like to leave them exactly oriented as they would be on the page, because we're going to see what happens when we rotate about the y-axis in the next video. It really doesn't matter. I think the picture is for you to help you visualize what's going on, because if you understand the concepts, you don't really need to memorize a whole bunch of crazy identities. If you think about memory, it's easy to forget formulas that have no meaning, versus if you understand what you're doing, there's no need to memorize, because you can just conceptually do the problem, and it's pretty much the same time, and honestly less risky than memorizing things that you don't understand, right? Okay, so carrying that concept forward, let's look at some specific examples. We're going to consider the region bounded by y equals e to the negative x, the x-axis, and the lines x equals 0 and x equals 1. We will find the Riemann sum approximating the volume of the solid generated by rotating around the x-axis. We will find the integral that will give the exact volume. So this problem, we're just going to focus on setup. We're not going to focus on actually computing this. We'll practice integration in the next chapter. So we're just going to focus on setup here. And in order to do these heavily visual problems, you do not have to be an artist. You just need to get enough of a sketch to help inform you as to what's going on. So we need our region. E to the negative x would be the e to the x curve reflected over the y-axis. So it'll look like this. And the x-axis, and x equals 0, and x equals 1. Okay, so there's our lines. And we're looking at the region that's also bounded by the x-axis. So to just shade that in really quickly, there's our region that we're looking at. So I'm going to draw in my rectangle. Looks like this is an example that touches our axis of rotation. So it looks like we're not going to have a washer here. We're going to have a disc. Now when I rotate that around, my little rectangle becomes a disc. So there's our little disc that we got by rotating around the x-axis. I should label the axes just to kind of remind you of that. Okay, so we are going to find, we're looking for the Riemann sum. So in order to find the Riemann sum, it's helpful to find the volume of the ith slice. Okay, so finding the volume, we need the area of the circle times the thickness. The thickness is a delta x. We can see because the width of the strip is the distance between 2 points on the x-axis. So that's the little cheat for that, the thickness dimension. So the volume of the ith slice is going to be, looks like pi times the radius of each of these discs, which is given by the distance from the x to the curve y equals e to the negative x. So it would be e to the negative x minus 0. So we don't no need to write that part. So there's our radius, pi r squared, times the thickness, delta x. And we're looking at the ith slice. So I'm going to add in those little I subscripts just to keep it consistent with our notation. Okay, so then the Riemann sum is what happens when you go ahead and add up all those slices. So I'm adding up. My index ranges from 0 to whenever you stop slicing. And as n goes to infinity, delta x will go to 0, remembering that n is the number of slices. So we end up getting the integral the integral, which is the exact volume. I'm writing this every time because I just want to really drive home that concept. So our delta x drops out. We get e to the negative x squared, which we can rewrite as e to the negative 2x. Just remembering our rules of exponents there. We're integrating with respect to x, and then we look at where do we start our disks and where do we stop it. So starting our slicing at the smaller x value, we go from x equals 0 to x equals 1. Trying to just anticipate some of the common concerns that students have with this concept. I think the biggest thing is that students really struggle with the just visualizing what these solids look like. And notice I did not draw the entire solid because yes, it is very hard to visualize, 1. And 2, it's hard to draw. And 3, it's not helpful to the problem. So I encourage you, unless it really, really helps you personally to draw out the full solid, please don't. I mean, I think that just drawing the slice is sufficient. And some people don't even need to draw this little picture here. But I do think it's helpful to draw the picture to just illustrate where the formulas are coming from. So remembering this is pi times the radius squared times thickness to give you the volume of that disk. Let's take a look at another example. So in our next example, we're going to consider the region in the first quadrant bounded by y equals 2x and y equals x squared. We're going to find the Riemann sum by approximating the volume of the solid generated by rotating around the x-axis, and then we will find the integral that would give the exact volume. So to do this, first we're going to need to get a handle on our region to help us figure out the dimensions of disks or washers or whatever ends up being generated. So in our first quadrant, we have a line, 2x, and we have a parabola, x squared. And I just so happen to know where these would intersect. They would intersect at x equals 2. So I know that my region is going to go from 0 to 2. And remember, we are rotating around the x-axis. So draw that in. And then I recommend drawing in your rectangle. So if you're going to use the left endpoint rule, the rectangle is going to look something like that. When it gets drug around, just remembering kind of what points informed the height of that rectangle. You're going to get what looks to be a washer because you see how there's this tiny amount of space. You've got a space between the parabola and the x-axis. So when you drag that rectangle around, you're going to get a washer. Actually, just to keep it consistent with our colors that we started in the beginning, let's do that one green. So when I drag that around, I'm going to have a washer. Doing my best here to draw the washer. Okay, see how we get the washer there? And I'll just remind us that that inner part is not actually there. It's not part of the area. Let's kind of go in and fill in some dimensions here. We've got our outer radius. Our outer radius is going to be, it's helpful to look at the rectangle for that part. The outer radius is going to be the point that's on the black line, 2x. So the outer radius is going to be 2x sub I if we're looking at just an arbitrary ith washer. And the inner radius is going to be the distance from the x-axis to this purple parabola. So it's going to be x squared, x sub I squared, if you will. Okay, so then when we go to formulate our volume of the ith washer, we have the pi times 2x sub I squared minus, so that's the area of the big circle, and then we're going to take away the area of the small shaded black circle, which is pi times x sub I quantity squared, pi r squared, and then multiply that by the thickness, which is delta x. So cleaning that up, when we write our Riemann sum, remember you can factor out the pi's and just have two x sub I squared minus x sub I squared times delta x, and our I ranges from 0 to n minus 1, where n is the number of slices. There's our Riemann sum, and to get our integral, we're gonna, again, what's gonna happen? As n goes to infinity, delta x goes to 0, and we can look at our Riemann sum to help us set up our integral. So we have pi, 2 squared is 4, so we have pi times 4 x squared minus x squared squared is x to the 4th. This is dx, and our integration is going to range from wherever we start our washers to where we stop them. So we would start slicing here at the left point of the region, and we would stop slicing here at the right point. So it looks like from 0 to 2. So there's our exact. Here's our approximate. And here is our volume of just one of the washers. So now we've seen an example of a disc, and we've seen an example of a washer that we would use when we are creating a volume of revolution rotating around the x-axis. So in the next video, we're going to cover what happens when we rotate about the y-axis, and I will see you then.